So let's start by trying to calculate the overall equilibrium constant for a reaction that is the sum of two or more other reactions. Let's consider again the reaction involved in the formation of photochemical smog. Let's consider at constant temperature the reaction involved in the formation of photochemical smog. In the first equation, nitrogen monoxide is produced in the car engines. Then in the second equation, we see that nitrogen monoxide is oxidized to nitrogen dioxide in the atmosphere. We have for these two equations the Kc values. For clarification, we are indicating here with a subscript which equation is. And the problem is asking us to calculate the equilibrium constant value for the reaction described here. So this will be our overall equation that we are trying to obtain. So let's check if both equations as they are correct in the sense that when you add them up, they allow us to obtain the overall equation. So what I like to do is to look at the reactants and product side in the overall equation and see if the equations that I have available I need to modify them in such a way, right, to get the nitrogen and oxygen in this case on the right side. So if you see both equations, okay, have nitrogen and have oxygen on the product side, so we are okay. And you can see if you add it up, you're gonna end up with 2 molecules of oxygen. And the other thing that I see is that nitrogen, right, is in the reactant side on equation number 1. So what I'm going to do is I'm going to add them up. So I'm going to start with the nitrogen in the gas phase, okay, plus 1 oxygen, right, from the first reaction in the gas phase, plus 2 nitrogen monoxide plus oxygen in equilibrium with 2 molecules of, or 2 moles of nitrogen monoxide in the gas phase plus 2 nitrogen dioxide in the gas phase. So if you see on both sides of the equation, you end up having 2 molecules of oxygen, so if you add them up. And the other thing that you get, right, is that species that repeat on both sides of the equation can be canceled, okay? So we're going to just do this, okay? And when you arrange it, right, when you arrange this equation, you end up having this. So we don't need to do any modification to equation number 1 and number 2. They're okay as they are. We're going to see another example that we may need to modify them. But for now, it is okay. So let's start by writing down the Kc expression for equation 1, equation 2, and the overall equation. So for equation number 1, we have, as usual, right, the products over the reactants. Make sure that you are using the coefficient of the equation to raise each concentration to its own power. We write down the equilibrium expression for the second equation. Then we do the overall equation, okay? So for the overall equation, it will be Kc overall. I'm just going to do overall, so we have a reference. Will be NO2 to the 2 over nitrogen times oxygen raised to the 2. Notice that if you look at the Kc overall, it's like we multiply each individual Kc, right? Kc1 times Kc2 give us the overall equation. So Kc overall equals, right, to Kc1 times Kc2, right? If we write down the meaning, right, the expression for Kc1 and Kc2, we end up, okay, having Kc1, NO2, nitrogen and oxygen times what is Kc2, right? NO2 to the 2 over NO2 oxygen. And if you notice, these terms cancel as we did right here in the equation, right, when we add them up. And if you notice, we end up, right, having the same expression. Therefore, because we don't have the equilibrium values, right, to determine the Kc overall, we do have the Kc1 and Kc2. So let's do the calculation, right? So Kc overall will be equal to the provided 7.2 times 10 to the minus 9 times 0.020. Okay, that means that the K overall will be 10 to the minus 10. Like this, we just, simplify the calculation of that additional equation, right, based on K values that we already know.